Hello. Today what we're going to talk about is the beginning of chapter 11, which is Intro to Calculus. So this is kind of a quick look at to what you're going to do next year if you do take calculus. So the whole word calculus, it means small stone in Latin. What we're essentially doing is looking at small pieces of a function or anything so that we can understand the thing as a whole. And there are three different parts to calculus. The first part is what we're going to start with, which are called limits. And essentially what a limit is you're approaching a certain value. And so sometimes you can't directly find that value. You will have to figure out what it should be as you get closer and closer and closer to something. And we're going to go through that today and for another week or so. The second part of calculus is called derivatives. And derivatives are used so that we can find the rate of change of a function, specifically the slope at one spot. So up to this point, you were looking at that you needed 2 points to find the slope of a line, and we only did slopes of linear functions. Now what we're going to do is find the slopes of parabolas and curves and different things like that, and derivatives is what allows us to find those rate of changes. And the last thing is called an integral. And an integral is to find the area under a curve. So this has a lot to do with looking at parabolas and different types of curved graphs and figuring out slopes, areas, limits, what they're approaching, things like that. So that's the basis of calculus, and like I said, we're going to start with limits. You're going to see a little bit of derivatives, but you will not see integrals until you are far into calculus, and actually Calc 2 is called integral calculus, so most of that is what all about integrals. But what we're going to start with, like I said, is limits. So looking at our note sheet that I have popped up right here, it says Introduction to Limits, Zeno's Dichotomy Paradox, and there is a TED Talk video that I think explains this very well if you want to jump over to that. It's just a quick introduction to where limits came from. And then come on back here and we will talk what a limit is. So a limit is a number that is being approached. Okay, usually it is a number. Sometimes it can be, does not exist. It could be negative infinity or positive infinity. Those are three other answers you can have as well. And it is a y value. It's a y value of a function. Now that you know what a limit is, let's go over some notation and the way that a limit is written. So you write LIM for limit. As a subscript, you have x that goes to a certain value, and that's the value that we want to approach of a certain function, and we're going to get out n, any kind of number or value. So the way you say that is the limit of f of x as x approaches c equals n. So again, we're approaching a number, an x value in a function to find its y value. And sometimes if you think about it like we've done up to this point, you would say it doesn't exist. Like there's an asymptote there or something different, and limits allow us to find that value even if they don't technically exist on the graph. Alright, example 1 of our limits. So we have the limit the limit of 5x squared as x approaches 3, and we want to see what is that equal. So there are three different ways that you can solve limits. The first and the easiest being direct substitution. Okay, so that means just like you've been doing with all of our other functions, when we have a value for x, we just plug that into the function and solve. So for this guy, we have the function 5x squared, and we want to see when x is approaching 3. So we just plug in 3 for x. So we have 5 times 3 squared, which gives us 45. So that means that our limit at 3x, or when x is 3, we're approaching 45. A different way that you can solve a limit, because sometimes direct substitution is not always possible, which you'll see later in these notes, is a chart. Okay, so when we're looking at our chart, we're going to have x and f of x. We're going to have x values that we're plugging into the function. We're not going to use 3, but we want numbers close to 3. So for example, like 2.99 or 2.999. You could forever say 2.99999 and, approach 3 but never actually get close to 3. So this is where we're approaching 3 from the left-hand side. You could also approach 3 from the other side. So 3.001. I'm run out of space, but another one that I'd put after that is 3.01. Just approaching 3 from either side so we can see if they end up in the same spot. So if you plug in 2.99 into your function, that 5x squared, you should end up with 44.7. If you plug in 2.999, you get 44.97. Coming from the other direction, if you plug in 3.001, you get 45.03. And so as you can see, what we're doing is seeing what are we getting closer to but not touching, and that would again be that 45 that we already saw by direct substitution. So that's the second way to solve. And the third way to solve is to graph it and see when I have 3 on my graph for my x value, what y value do I end up with? And if you graph this as a parabola, you'll see that you'll get the point 345. So, like I said, if direct substitution doesn't work, that's when the chart or the graph would come into play. However, if direct substitution works, go ahead and do that. And you don't have to show all 3, just one to help you find the answer. If you want to take a second to try and figure this one out, you should pause the video and see what you get for the limit of this one. So for number 2, we want to find the limit of x squared plus 5x plus 4 over x plus 4 as x approaches 2. And so this one can be solved by direct substitution, since when you put 2 in the denominator, it doesn't give you a 0 down there. That's the only time when direct substitution is not going to work. If you plug in x and you get a 0 in the denominator, that would be an error if you typed in the calculator, or that does not exist. Here it does, so we can use direct substitution, and you should end up with 3 as your limit for number 2. Alright. Next one, we want to find the limit of g of x, where we're told that green over there, that green function, g of x is x squared minus 6x plus 8 all over x plus 2. We want to find the limit of that function as x approaches 2. And so let's see what happens if we use direct substitution. So if I plug in 2 for x, I get 2 squared minus 6 times 2 plus 8 all over 2 minus 2. And so that's going to give us a 0 on top and a 0 on the bottom. And so this is where direct substitution does not work. And we know from looking at rational functions earlier in the year that this means that there is a hole in the graph. So since direct substitution doesn't work, we want to try one of the other ones. We can either use a chart or we can use the graph. And since I have the graph already up here for us, that's what we're going to follow right now. And so there is something called a left-hand limit and a right-hand limit. And we look at those, so we're approaching from either side, from the left side and the right side, and that's going to tell us what our limit is for the overall function. And so if we are looking at just our left-hand limit for a minute, that means that we're going to look at the limit approaching 2, and we put a little negative up there to say we're approaching from the negative side of our g of x function. So the left-hand limit, we're coming from the negative side, and so what we do is trace the function from the left to the right until you get close to where that x value is under our limit. So you're going to trace from the left-hand side to the right until you get to about 2, because that's what the x value that we're looking at is. And so if we get to 2 as our x, we know that our function, or our limit answer that we're looking for, is that y value. So that would be at -2. So as we approach 2 from the negative side, that gives us -2 as a y value. So that's what our left-hand limit equals. For our right-hand limit, we're going to do the same idea, but we're going to be approaching 2 from the positive side of our function. So we want to see what that equals when we come from the other side. So right to left is what we're doing. Going back up. So we're coming from the right side to the left until we get to about 2 as our x value, and we see that we end up in the same spot. So here, my limit, my right-hand limit as I approach 2 from the positive side is also -2. Since those numbers are the same, that means that that is exactly what my limit is approaching. So the limit of g of x as x approaches 2 is -2, and that's because our left-hand limit and our right-hand limit had the same output. Okay, so one way of doing that, here it says you can work around a point of discontinuity. And so what that means is the point of discontinuity is that hole that we have in this linear looking graph that we're looking at. And so to go around that, you can do it algebraically. So if I rewrite what our equation or our function is here, I have x squared minus 6x plus 8 over x minus 2. To do it algebraically, what we're going to do is factor and cancel anything we can. So if you factor the top, you should end up with x minus 2 times x minus 4 all over x minus 2. Okay, and think back to when we did rational functions and we were graphing them. If you had the same binomial on top as the bottom, that told you you had a hole in the graph. And I'm running out of time for this one, so watch for the next video and we will continue.